All right, guys, we made it to the most exciting part of the course, the inferential statistics part. We're no longer just describing data. We're not just seeing if two are related. Now we're going to look at data and determine whether or not we have support for a hypothesis. We're looking for data that demonstrates causality. This caused this, right? That's huge. How do we get there? What's the transition from descriptive to inferential statistics? Well, in large part, it revolves around the normal curve, right? The normal distribution, that bell-shaped, unimodal, symmetric curve that we know so well. Now, we've talked a little bit about how you can use positions under the curve to represent percentiles. So if you're, say, a z-score of 2 or 3, then you're that much further from the mean. And because the curve gets thin there, we know that's a far less probable thing to occur. What we're going to try and do now is use that normal curve to predict all the possible events that can happen, all the really common ones that happen near the center, right near the mean, right? If you measure the average of any individual you find on the street, height, they're probably pretty close to the average height. And every now and again you find these really, really extreme versions of those, right? So we're going to use that normal curve that represents all the possible scenarios and see, did we find something way over here? And it's very unlikely to happen. Did we find something way over here? Again, unlikely to happen. Or did we find something in the big bulk of the curve in the middle where basically everything takes place and is pretty expected, right? Highly probable events. We know this curve and we know where all these cutoffs are largely because of gambling. This guy, Abraham Demoivre, I'm probably butchering the guy's name, but I never took French, essentially mathematically defined this thing a long time ago, right? Several hundred years ago, and it was sort of forgotten for a little while, and then another sort of probability mathematician, philosopher took it up and sort of helped to extend it even further into basic probability today, and now we use it essentially in virtually all forms of statistics, okay? And that's across fields, right? When scientists in chemistry are looking at their data, they are essentially relying on things like normal distributions to analyze the differences in their data as well. So what do we know about that normal curve? Well, first of all, it's basically everywhere, okay? I mean, functionally everything will take on the shape of a normal curve. You could say the approximate temperature of a mug of tea. If I had 100 mugs of tea and I took the temperature of every single one of them at once, most of them would be pretty close to whatever the average is of all of those cups of tea. But then there'd be one or two that'd be really cold, and there'd be one or two that'd be really hot, maybe based on their position. But those would be super unlikely events, right? And so that normal curve, I mean, almost anything we could possibly plot comes in a normal curve. I mean, look, check it out. Heights of 14-year-old girls. Distribution of pizza delivery times. SAT scores in 2020. Female shoe sales as a function of shoe size. Housefly wing lengths. Number of years worked for employees at a cereal factory. Egg diameter for rainbow trout. Okay, you get the point. Lots of things are represented by this normal distribution. Whatever the average is for a sample or population, most things are near the average, and very few are way above or way below the average, making those events very unlikely events. Okay, so it's everywhere. The other thing is that because we know about the standardization and definition of that normal curve, right, we sort of relied on this when we looked at z-scores and z information, the bell shape then can be translated into percentages, right, the basic process of standardization. So if we look at, say, a normal distribution of IQ scores, you see that most IQ scores, right, 68% of individuals fall right between an 85 and a 115. The mean is 100, right, and so the standard deviation then of 15. Most of us fall within one standard deviation of the mean. Going out to two standard deviations, then all the way down to 70 or 130 in raw scores, that now captures, 95% of that population. Right, and you can see then by the time you get out to 3 standard deviations, you have 99.78 or something like that percentage captured within that distribution. That means it's less than 0.1% on either tail that are 3 standard deviations from the mean. Right, it's unlikely, super unlikely to be that low or that high in intelligence. That's why we don't have a lot of people out there with incredibly low intelligence or incredibly high genius level intelligence, right? Those are the unusual circumstances. Unfortunately, it'd be nice to have a few more geniuses out there. The last thing that we can really talk about is the way in which the normal distribution aids in inferential statistics, right? The basis of inferential statistics is what we call the central limit theorem. And I'm going to give you a couple of different exposures to the central limit theorem to hope that you sort of get it. Essentially what it says is that even if a distribution of raw scores is skewed. So let's say I take that sample of teas, right? And I get the temperature of all these mugs of tea. And they're all basically around the same temperature. But then there's one or two that are super cold. Maybe when I wasn't looking, somebody threw an ice cube in it. But for whatever reason, those temperatures are way out to the end. So instead of it being a normal distribution, it's super skewed. Now, if I take that 100 teas, and instead of looking at all 100 of them, I just take a sample of 20. And then I take another sample of 20, and another sample of 20, and another sample of 20, and I just keep doing it, randomly taking which 20, replacing those teacups again, so they might get picked again in the next sample of 20, and I keep doing that. If I take the average of all of those averages, so the average temperature of these 20, the average temperature of these 20, the average temperature of these 20, that average of averages will be normally distributed, even if some of those sample means were skewed. Right? Even if that distribution of these 20 had a horrible skew because of that ice cube cup, it doesn't matter. As I take the average of all the averages, we get a nice normal distribution again. That is the central limit theorem, and it says that occurs as long as the sample that you take, right, the number of mugs, the number of tea mugs that I look at, exceeds a certain value. So essentially, while it doesn't specifically state this in central limit theorem, that number is about 30. Right? It's kind of a magic number in statistics, if you will. When we reach about 30 observations, then it doesn't matter if that distribution of raw scores is skewed. The distribution of sample means, which we'll talk about in a subsequent video, will be normally distributed. The higher the sample size is, the more likely that that distribution will be normal and a little bit more narrow, less variability, right? Meaning almost everybody is close to that mean. So you can see a sort of demonstration of this with sample size, right? So here's a sample of heights. These are 140 hypothetical students and their heights in inches, right? Just like we did earlier on in the semester when we looked at our descriptive statistics of heights of males and females in our class. Now, if I were to take a sample size of 5, any random 5, and this is just one distribution of a random set of 5, it might look like this, right? So we've got 3 individuals that are about 62.5 inches, that's probably pretty close to the mean, and 1 individual that's pretty tall and 1 individual that's reasonably short. How about if I took a slightly larger sample of that? So instead of 5, I do 30. Now you can see that because most individuals are relatively close to the mean, the center of the distribution, they start to pile up there. Few rare observations are occurring because, why? They're rare. It's unusual you have somebody that high above the average height or that low above the average height. And if we take an even larger sample size, this one up to 140, you can see that it just becomes more and more normally distributed. And this is just a distribution of raw scores, right? As I said, if we took the average of this, which looks to be probably around 65, and then we took a sample of a different 140 students and then another 140, and we compared all those averages, we would find that that distribution of averages was normally distributed. That's the central limit theorem. And you can sort of see this development of that normal distribution with sample size in something that Francis Galton actually came up with, back in the 1600s maybe? I can't recall when he lived. It's called the quincunx. And if you remember the old TV show that featured Plinko, or the sort of game that you might be able to play at home because there are home versions of Plinko, then the quincunx might look a little familiar. So let me show you an example of that. So this is an example of that Francis Galton quincunx that I was talking about. Let me speed it up a little bit and we can see, essentially it's like that Plinko game, right? So a ball is dropped and it hits these and will randomly either bounce left or bounce right. And you can see as they start to add up, they start to fall into these bins for where they happen to fall, all the way over at the 0 end or the 6 end. Those are way off to the left or the right. Right, 1, 2, 3, 4, 5, getting closer and closer to the center. The point is that as more and more of these balls are added, you can see them start to become more and more of a normally distributed shape. So what I'm going to do is I'm going to increase the size here. We're going to leave the left-right balance at 50-50. That means its probability of bouncing left is 50%. The probability of bouncing right is 50%. Let's up the speed all the way, and let's restart it so we can see what happens. You can see how quickly these things start to go. In fact, here, let me shrink it back down again so we can see this. Right? You can see that as they pile up, they begin to create more and more of this normally distributed shape. When we have only 16, 17, 18 observations, it's not quite normal, but as we get closer and closer to that 30 number, notice it becomes more and more normally distributed. As we go way and way above that number, it becomes even more of a normal distribution, right? This is a good example of how increases in sample sizes will sort of result generally speaking, in this more normally represented or distributed representation, right? We talked about this a lot in central limit theorem. Larger sample sizes lead to normally distributed distributions of sample means, and the quincunx is just sort of one of the ways in which Galton kind of explained this concept to others. We can see now that upwards of 170 observations, we are definitely in the world of a fairly normally distributed shape here. So that's it, just a quick example. You can find this on mathisfun.com if you want to play with it yourself. All right, cheers. All right, so that was it. You don't need to watch the quincunx for 20 minutes to get the idea of how it works. So that's the intro to how inferential statistics work. We got 2 more videos here, so buckle up and let's go. Cheers.